fact, if you Google these, you find there's a large literature on it. There are even books written on it. They're surprisingly complicated. So I'm going to write down two different versions. So first one is, say I have a bilinear form from V cos V into W. So skew and bilinear. And then define a Lie algebra, which is V plus W, such that W is the center of G, and Lie bracket between V and V lies in W, and it's given by VW is equal to V of VW in W. Right, so everything else is 0, because W is the center. So it's a Lie algebra, because the co-identity is trivial. If I take three Lie brackets, I always get 0. So every skew-symmetric bilinear form has associated to it an interesting Lie algebra. This is called two-step nilpotent. Two-step because after I take brackets twice, I get 0 already. It's kind of the most trivial nilpotent Lie algebra one can think of. So that's one way of formulating. I like to formulate it. Oh, and I can also assume that E is non-degenerate without loss of generality, because if it wasn't, the center would be bigger, right? There's a W where this is 0 for all V, then the center is bigger. So might as well put it in W. So it's a skew-symmetric bilinear non-degenerate form. So the equivalent way of formulating that is to put an inner product on V plus W, such that W is such that V is a orthogonal complement of W. So make it orthogonal, otherwise doesn't matter. And now I define a map I called J last time, from W into the set of skew-symmetric matrices on V, which V has an inner product. So this makes sense, which is linear and injective. And I think I need that also, we'll see in a minute. And J of W is invertible. So skew-symmetric invertible matrices. That's what I want the image to be. This condition by itself already is strong. So just to have, say, in the matrix algebra of skew-symmetric matrices, that's a vector space, right? I want a linear subspace such that every vector in linear subspace is invertible. It must be linear. They can't be very big. V can't be very big. We'll probably talk about that later on. It has to do with Clifford modules and Clifford algebras and all kinds of things. Anyway. And now I define, so again, W is the center of G, like before, right? Bracket between V and V lies in W, as before. And now defined as follows, that J of W, bracket with applied to V, bracket with W. What am I? Sorry. I want to define the Lie bracket, right? So I take a Lie bracket with two vectors in V. Well, W lies in W, so maybe UV. I take an inner product with W. Now let that be J of W, the central element, applied to U comma V. So this defines the Lie bracket, right? Because I describe the inner product of everything in W. That determines this uniquely as an element of W, right? It's skew-symmetric in U and V because J of W lies inside the algebra of skew-symmetric matrices. So it makes it skew-symmetric. Now it's a Lie algebra. And let's see, I think I want JW to be invertible so that the center is W. So let's think about this. But if there was a W set JW applied to U is 0, so it's not invertible, then this would say the inner product with everything in V0, which is a Lie bracket with everything in V0, then it lies in the center. Right, so this here guarantees that W is the center of the Lie algebra. So if I want to, I can always achieve that as before. So it's an equivalent way of formulating this here just by using inner product and skew-symmetric matrices, which makes it a little bit easier to work with, I think. So then this is a group of generalized Heisenberg type. I can make another additional assumption, and I say then it's of, so this was a generalized Heisenberg group. Then I say G is of Heisenberg type. If the following thing is satisfied, so maybe here one should call this, this here is H of the bilinear form B, right? And this here is, G. And this here is G of the endomorphism J. G is a Heisenberg type if this endomorphism, this linear map J satisfies that square is equal to minus norm W squared times identity. So this here just normalizes it. It's supposed to be linear in W. So if I multiply the constant, it has to come out as a square, so I'm just normalizing. Particularly if I take a vector in W of unit length, then I get an endomorphism whose square is equal to minus identity. So it's a complex structure. And it's Q. So I get a skew-symmetric complex structure. So what does that mean? I claim I can express this in a different way. So let's say I have let's call it L for the moment. I have something that's a complex structure, and it's skew. Then I claim it's also orthogonal. As transfer is minus L. L squared is minus identity. So it's identity, so this means that L is in the orthogonal group of the vector space V. So it's skew-symmetric, it's orthogonal, and it's a complex structure. So I claim an equivalent way of saying this then is that J of W is an orthogonal complex structure. Of course, I can go backwards, right? If it's orthogonal with this identity, and this is also true, then this must be true, and it's skew-symmetric. And I prefer to look at it this way, that it's a complex structure that's not symmetry. For me, that's more geometric. That's the same thing as saying that it's a complex structure and it's skew-symmetric. So in other words, what I have on this vector space V, right, the act on V, I have a bunch of orthogonal complex structures, a linear subspace of orthogonal complex structures. That's what I have on this vector space V. And that's a really interesting structure. So let's give some concrete examples of these Lie algebra Heisenberg type. So I want to look at the special case. Examples of 3. So you have to specify this linear map J. So first example is going to be the Heisenberg group itself. So I take Cn plus R. So that's my V, that's my W. Okay, it's going to be the Heisenberg group. And the map J is, I have to apply to something in the center, right? It has to be on here an orthogonal complex structure. What could it be? Multiplication by I. Right? This is just norm t times the left multiplication by I, if I want to write. That certainly respects the norm. Square is -1, so it's an orthogonal compact structure. And I only need one, but the center is one dimension, and actually need one. Okay. So now notice that if I write Cn as Rn plus Rn, then this will be a vector u comma v. Then what's the okay, so let's as a basis write u1 up to un, v1 up to vn. It's an orthonormal basis of each component. And then I claim, notice that if I take v bracket of ui with vi, inner product with t is going to be j of, so of course I can take the inner product 1, right? That determines already. I don't have to take it with t.
We shouldn't take the modules.
Pardon?
We shouldn't take the modules in t because it must be linear.
That makes it linear. Why? So multiply by constant comes out as a constant. Thank you. Absolutely. No absolute value. Thank you. So apply to t equal to 1. This means I take I of ui, inner part with vi. And here I chose my orthonormal basis such that the compact structure on Cn has this usual matrix that we've used many times before. So that means that j of ui is vi. So that means this is 1. So that means that ui vi bracket is equal to, say, let's call this r times t, the generator, is equal to t. Now if you go through the same rigmarole, ui vj is equal to 0 when I is not equal to j. Of course, j ui is vi, and that's has inner product non-zero whenever I is different from j. Yes? Pregunta? No? Everything?
I was asking what is the Li?
So forms, of course here I wouldn't have to, as just I times. I wouldn't have to use this word, right? But later on this is going to be convenient. So this is a map from Cn to Cn, which takes u to iu, which is multiplication by I. Okay. This notation is going to be convenient in a minute. So now you can see the structure of the Heisenberg group. Right? It was of this type. This is my Rn. This is an Rn. That's my R here. Bracket of these going here. That's exactly what it does. So you can now see the structure of the n-dimensional Heisenberg algebra. I only describe the algebra, so I'm not going to try to describe the group itself. You can also do that. But I'll just describe the algebra. Okay, so that's the simplest kind of example. It really generalizes the Heisenberg group, and that's why it's called Heisenberg type. Now, so I shouldn't erase it. Remember, we want to satisfy the identity j at w squared is to the minus norm w squared times identity on the vector space V for all w and w, which was the center of G. So next example. Let's take Hn plus, and now I'm going to take the imaginary quaternions. It's kind of an analogous here. I take Cn, and that's the imaginary complex numbers if you want to. It's just R. So that's my V plus W. And now I have to map from, now I need to map from Im-H into the skew symmetric matrices on Hn. Now you can imagine what I do, right? I take Q, I take it to J of Q, which is left multiplication by Q. The guy is enough from Hn to Hn. Since I claim that's an isometry, right? If I take a vector v and take to Q times v, then the norm of QV is the norm of Q, norm of v, and that's norm of v, because norm of Q is equal to 1. Okay, so I should not take, that works when the norm of Q is equal to 1, otherwise I multiply with the length of Q in front of here. Maybe that's a little better. So define it for all imaginary quaternions. So so now I get norm of Q times norm of V, and I don't even have to say that, so what should I say? Since Q is imaginary, LQ is Q symmetric. And what is J squared, right? J of Q squared. So it is norm Q, LQ, LQ. So that's norm Q left translation by Q squared. But what is that? So remember that Q bar is minus Q, because QL is imaginary quaternion. So Q bar is minus Q. So norm Q, here left multiplied by Q times Q, but Q times Q is minus 1, right? This is minus Q bar, sorry. Because Q bar is minus Q, but Q bar is a norm. May have done, it's minus norm Q, oops, 1 power too much, right? Should be the square, not the cubed. Where did I, should I have not taken the...
Again, should we erase, in this case, not only the modulus, but modulus Q? Because if we have only left multiplication by Q, we have left multiplications times Q squared, and that would be minus modulus square identity.
When Q is norm 1, you mean?
In general, yes.
Just do this.
Just left multiplication.
Absolutely. Very good, very good. Now I'm fine. Now he saved me. And now it's a square. Otherwise, it wouldn't be linear again, right? Same problem as before, it wouldn't be linear. Okay, so this thing is a complex structure, right? L squared is minus identity. And it's also skew symmetric. So it satisfies these. And of course, it's always an isomorphism, right? LQ is an isomorphism. So these things in here are also isomorphisms. That's kind of like a somewhat more interesting or more complicated V algebra than the Heisenberg group. Let's say in Heisenberg group or the quaternions. But now you can do the following. That's really subtle. I take Hn, like some Hn, plus imaginary quaternions. This is my W, and that's now my V. And my Q, so I have to go from H now into H plus Hn. What's skew symmetric matrix on this vector space? So I take a Q in here. And now send it into LQ, RQ. So I operate in the first component on the left and the second component on the right. So I claim if I do it here, so it's not hard to see if I did here RQ instead of LQ, I get the same D algebra. Here it doesn't matter. But now I do it in a different component here, and that's different. So I claim it's not isomorphic to the one where I would write an LQ here. It's a different Lie algebra. Really subtle. Because the quaternions aren't commutative. Right? And whereas over here, if I replace this by an RQ, I get the same Lie algebra. And this has geometric properties that I want to mention in a minute. Maybe one more. You can imagine what I do next. Cayley numbers, right? So plus imaginary Cayley numbers. And I'll do the same thing. JFQ is equal to LQ. Be a little careful because K numbers aren't associative, so we have to check whether I need associativity or not. Well, so what is LQ squared? So acting on a Cayley number U, that's QQ times U, but that I can switch, I claim. This is Q times QU. Of course, I should do the other way around. So what does this mean? I do it once, then I do it again. But that's the same thing as putting it around this here. Has anyone worked with the Cayley numbers? Why this is true for the Cayley numbers? So it's not associative, but it has a property if I take two Cayley numbers, then it's associative. Everything spanned by two Cayley numbers is an associative algebra. In fact, it's isomorphic to the quaternions as an algebra. So here I can do that, right? And of course now Q squared was again minus 1 times norm U. Let's see, what did we do? Oh, no, sorry. It's minus norm Q squared times U. That's what we just did, right? Because Q bar is minus Q. So it's satisfies the identity, right? And again, it respects the length, so it's an orthogonal map, right? And these are orthogonal compact structures. Because there are no other division algebras, at least here we used. Here it's also important that for the Cayley numbers, you still have the identity that the length is preserved. Right. That we've used somewhere. That's true for the Cayley numbers. It's called a norm division algebra. But if you look at norm division algebras, then there's a theorem, I forget whose theorem it is, that the only ones are R, C, H, and the Q numbers. These are the only norm division algebras. If I take the norm away, there are many others. They're complicated division algebras, but normed ones only those. But I can crank this up, and then what I do is called Clifford modulus. So not division algebras anymore, but Clifford models. That's what this is an equivalent way of describing what a Clifford model is. So you might do this at some point later on when I talk about spin groups. That's what you have to do if you want to talk about spin groups. Maybe one more comment, which kind of makes this structure interesting. So again, looking at this example over there, right? So where JW squared is minus JW minus W squared identity, right? So I do the following. Take the unit sphere inside V or W, let's see. inside W. So in other words, I take Q in W is length 1. Because now these are complex structures. Sorry. I call them W here. Keep my notation consistent. Now these are complex structures. And now I claim I can construct in W, V or W, let me see. I want to construct linear independent vector fields on spheres. I claim this kind of structure here gives rise to linear independent vector fields on spheres, either in W or in V. Well, the thing operates on W. Sorry, it operates on V, so it should be unit sphere and V, I think. Let me try that. Now I want to define vector fields on the sphere by sending. So what's the tangent space at V of the sphere? It's simply V perp. It's another orthogonal vectors to the radial vector are just the tangent space. So I define vector fields. See for each
line in W, we will have a vector field.
yes. So for each Q in W, I take the vector field, say x sub Q, which apply to a foot point in the sphere. It's supposed to be vector field in the sphere, so I have to apply it to a foot point in the sphere. It's supposed to lie in the tangent space, must be orthogonal to it, and I send that equal to J of Q times V. Right, notice this is orthogonal to V because JQ was Q symmetric. So I get, and of course it's non-vanishing because J of Q was invertible. Right, so notice that XQ at V is non-zero for all V. And even more than that, if I take, say, Q1 up to Qn, a basis of W, then I get a vector field x1 up to xn, left multiplication by the j of those elements. I claim these are linear independent. On the sphere Sn. Because this is not the same n. It's a dimension of W. And here n is a dimension of V, so it might be better to call this Sn minus 1 and call n the dimension of V. So V is n-dimensional, W is m-dimensional. I get vector fields on Sn minus 1, which are non-vanishing at every point and are linear independent at every point. This is a famous old problem. What's the number of linear independent vector fields on spheres? It's a very old mathematical problem. This was solved in somewhere around the 50s. It was the first success of K-theory. So the proof goes via K-theory. And so there was a conjecture how many there are for a long time before that. And they come exactly from the structure. So this structure here gives you, this structure here gives you a certain number of linear independent vector fields, and that's the maximum you can get. And you can write down to see the numbers that you get if you want to call they have a certain name. And then it took a long time to prove that that's exactly, you can get more than that. And this was the first success of K-theory. Okay, so another interesting context where these arise is in geometry and harmonic analysis. Of course, so I have this Lie algebra G, say, associated to J. Of course, this corresponds to a Lie group. Unique simply connected Lie group with that Lie algebra. And that's a nilpotent Lie group then, because the Lie algebra is nilpotent. And I have an inner product member on the Lie algebra G. And this defines a left invariant on the group. Just by pushing around that inner product and the Lie algebra with left translation everywhere. So I get a left invariant on the group whenever such a structure, and one can try to look at the geometry of this left invariant. And the examples are the following type. So I don't know if you heard what a manifold, or a Riemannian manifold is that is harmonic. If either one of the following two equivalent definitions satisfied. So in harmonic analysis, one often describes it like this. If a function f on the manifold is radial, then Laplacian of f is radial. So radial means in the sense I pick a point, right? The function only depends on the distance to the point, right? And for that kind of function, if I take the Laplacian, it again has a property that it only depends on distance to the point. So that's a very useful kind of thing in harmonic analysis. And the claim is that this condition is equivalent to the following. For all p and m, a ball of radius, small radius around p, has constant mean curvature. Because depending on the radius that I choose, so I choose small balls, so it's a real ball, right? No singularities. The boundary of the ball, sorry, the sphere. So let's take a small ball as well out, take the boundary of that. I got a sphere around the origin. That's a hypersurface in the whole manifold. A hypersurface has a mean curvature. And acquire that mean curvature to be constant along the sphere. And I change out the constant changes. But along each sphere, there's constant mean curvature. Turns out that condition is equivalent to this kind of condition that Laplacian of radial is radial. So there was a conjecture, a long-standing open conjecture. Dietrich-Nerowitz. Which says that if M is harmonic in that sense, then M is isometric to a sphere of constant curvature, proportional RPN, or CPN, or HPN, or what's called the Cayley plane. And these are natural, they all have natural metric on them. So like for CPN, there's something called a Fubini-Studi metric. It has a very nice geometry, a very natural metric. There's an analog of Fubini-Studi for here and here also. Right? So these have all canonical geometric structures associated to them. And the space harmonic if and only if it's one of those. And these spaces are harmonic, and conversely. So converse is not hard. Because you have lots of isometries. That's why. In fact, I claim it's kind of obvious, right? In the sphere, of course, the distance spheres are small circles. They clearly have constant mean curvature. In CPN, you have enough isometries so that for each vector, there's some isometry that takes it to another vector. So an isometry would take a ball to a ball and would preserve the mean curvature. So therefore, it's constant. So these easily have this kind of property, and that's supposed to be all of them. Then there are two results. So one was a theorem which is due to Zaro, which says if M is compact and simply connected, and M is harmonic, then the conjecture is true. So in the compact case, okay, so here maybe I have to add some other examples, maybe non-compact ones. How should I write H complex? So for each one, there's a corresponding non-compact one which has the same kind of geometry. They're also harmonic. So in this category here of compact ones, which are simply connected, that's it. We proved that. And then there are counterexamples. Due to Damek and Ritchie. And for example, this example that I wrote down a minute ago, where I took LQ, RQ, I reversed the two things on HM plus HM, this is harmonic. It's not isometric to one of these manifolds here. And now these manifolds have been studied a lot in all kinds of different contexts. They're often a good source of counterexamples. So the interesting things that come up all over the place. Okay, so let's look at some more examples that almost look very easy and trivial because 3 times the Lie bracket is 0, but even that has interesting geometry. But they're classified in terms of Clifford modulus. So these are classified. If I look in general at meaning these ones, these are classified. The more general ones, where I take an arbitrary bilinear form and look at the corresponding nilpotent Lie algebra, they're not classified, only low dimensions. So even these kind of two-step nilpotent Lie groups are not classified. Kind of surprising. Okay. So last subject in this example section is coverings of classical Lie groups. So there are all kinds of interesting coverings that one often works with that you should know about. Let me remind you that if I have a covering of Lie groups, then kernel of the covering is a discrete subgroup of the center. And conversely. So if gamma lies in the center of G tilde and is discrete, then dividing by it is a covering. So we classified coverings in that sense in terms of the center, right? Another property that I'm going to also use is that pi is a covering if and only if E pi is an isomorphism. So that's something else we proved. Okay. So simplest example is that SO3 is RP3. It's a real projective 3 space. There are various ways of seeing that, but my favorite way is by using quaternions. So take a unit quaternion. Okay, and now define a covering, and we call it pi, from S3 to SO3. So take a Q inside S3. You got S3 as a subset inside all the quaternions. Now I want to send it into an orthogonal matrix, and here I take I regard SO3 as a orthogonal group acting on the imaginary quaternions. And I take as an endomorphism here, V goes to conjugation. Which is the same thing as Q inverse. Notice that this map here, so let's call that CG. So CG takes 1 to 1. And CG is orthogonal because Q is a unit number again, and therefore CQ takes imh to imh. So it preserves this three-dimensional subspace here, and also it preserves the length, right? CQV. Is norm Q, norm V, norm Q bar, so it's norm V. So it lies in a orthogonal group, so the image lies in here indeed. Well, so this says that CQ lies in O3. It preserves length, right? But S3 is connected, so pi of S3 is connected. So it actually lies in SO3. So the identity of O3 with SO3, which we proved. Okay, so now I want to show that's a covering. So what was the recipe? We're supposed to look at the kernel, right? Here's the kernel determines the covering. So what's the kernel of this covering? So it's a set of all quaternions in S3 such that QV is equal to minus QV if you want to. Right? That's Q bar V. Is that what I want? No. So QV, Q bar is V. So kernel of the covering, so it's supposed to be 1 here. So QV, Q bar is V. So which means that QV is equal to VQ. Right? So what quaternions commute with the unit quaternions, right? So what quaternions commute with, so V is an imaginary quaternion. What quaternions commute with IJK. So V and H commutes with IJK. Because that means that V is plus or minus 1. It can't be in imaginary quaternions plus or minus 1. Of course, if it is plus or minus 1, Q. If it is plus or minus 1, then certainly it's identity. So it's exactly the kernel. Inside the unit quaternions. So that's it. Now I have a covering, right? The kernel is finite. It lies in the center, certainly. And it's a twofold cover. So that means that the image, so pi of SO3, is equal to S3 divided by the kernel. So that's S3 divided by the integral map. And that's by definition RP3. Right, so there's a very nice explicit map from S3 to SO3, which is, it's a cover, right? S3 is simply connected. This here was a Lie group because unit return is of length 1 and it's a Lie group. The kernel is just plus or minus 1. So that means that this thing down here, which is the image of the covering, is just RP3. Is that a question?
Yes. To prove that it is onto, we must say it's a covering.
So I claim we have that already. What do I have to add? I know the kernel of pi is Z2. This, of course, implies here that d pi is an isomorphism. Right? What else should I add? And so I know that d pi is an isomorphism, is injective. The kernel is finite, right? That means the derivative is injective, but they have the same dimension. So this and dimension S3 is dimension SO3, which is 3. Right? So I have to add that, right? So that's why I'm using this property also. This is very nice. And of course, once I have a covering, it's onto. So I don't have to check it's onto. Follows from the theory. Right. Have you seen another proof before that SO3 is RP3? There are other ways of seeing that. More geometric. What does an element of SO3 look like? Rotations in 3 space, what do they look like? To S2, that's another way to describe RP3, that's true, but I want to look at SO3, right? Look at rotations. How can I describe rotations? It's in 3 space, that's important. How do I rotate something in 3 space?
An axis.
Exactly, right? Rotation has to have an axis. That's a small linear algebra exercise. There must be an eigenvalue of eigenvalue 1. So that means rotation must fix something. There must be an axis. And of course, it rotates orthogonal to that by a certain angle. Right? So that's how I can describe rotations, by an axis and the angle that rotates around it. I want to show that's RP3. So I have my axis here, and I have my angle. Angle, say, lies between 0 and 2 pi. Or maybe better, between minus pi and plus pi. Just a question of normalization. Okay, so that looks like, and of course the axis doesn't have a length, it only has a direction, right? That's an RP2 if you want to, right? The direct lines in R3, that's an RP2. That's not what you want though. And then I have another product with the angles if I want to. There's a better way to look at this, to say, well, this is, I can identify this with a unit 3 ball, with the identification that V goes to minus V when V has length 1, by doing the following. So given vector in the unit ball, given a point in the unit ball, what rotation is that? Because that's the axis, clearly, right? And the length is the angle. Right. The angle lies between minus pi and plus pi, so it's actually a ball of radius pi around the origin. Right? So, and then I have minus pi here. So it looks like a ball now. SO3 is a ball. That can't be. So what identification is this talking about? Why is this what I have to identify things? I have an axis I rotate by an angle between minus pi and plus pi. If I do it by pi, it's the same thing as by minus pi. Right, so on the boundary, this rotation and this rotation is the same thing. That's an axis, here rotated by pi, here rotated by minus pi. It's the same thing. So on the boundary, in the interior, it's well defined. But on the boundary, there's a choice, or there's an identification. And then if I take a 3-ball, identify the boundary with antipodal points, that's another way to describe RP3. So this is an RP3. Well, it's another way of seeing this fact. Now, more geometric if you want to. So I like this better because it's geometric, but if you want to work with the covering explicitly, then you have something that you can write down and actually do computations. Okay. By the way, so another consequence of this here is the following. So S3 is the universal cover of SO3. So S3 is simply connected. And what's the center of S3? Well, we just talked about that everything that commutes with a unit quaternion must be real. So this has to be plus or minus 1. So it's isomorphic to Z2. This implies now that the only Lie groups with Lie algebra SO3 are S3 and SO3. There are only 2 Lie groups of that Lie algebra. Everything was obtained by the universal cover by dividing by a discrete subgroup of the center, but the center is only Z2. So either nothing or all of it, and then you get those 2. So tell you kind of the general strategy of how would I determine what all Lie groups look like with a certain Lie algebra. You have to somehow find a simple model, then compute its center, and then divide by the various center subgroups. But in general, what can be subtle is that if I have a big center, it could happen that if I divide by different subgroups of the center, that the nebula is isomorphic. That can happen. That's what the next example shows. Namely SO4. Okay, the universal cover of this is S3 plus S3, which of course is also, again, a Lie group in its own right. If I look at that unit quaternions. So suppose universal cover, so you have to write down a covering. Turn this into SO4. And I kind of mimic the same thing as before, but now this is the orthogonal group of the quaternions. It's 4-dimensional. Here I take a pair of quaternions, I send it into a linear map which takes V to Q1V, Q2 inverse. These are unit quaternions. That means that the length of this is the same thing as the length of V, right? So it's orthogonal. This is connected, must lie in SO4. So certainly tends into SO4. Things like this are also homomorphism, right? So get a homomorphism. Then what's the kernel of pi? So kernel of pi. V here is an arbitrary quaternion. When do I get identity? So when is Q1V equal to, bring it on the other side, V2, Q2 for all V. This is supposed to be V, so I put Q2 on the other side. So this must be true for all vectors V. So fix the Q1 and Q2, 2 unit quaternions, and when is this true?
They must be equal.
Because, take V equal to 1, they must be equal. And then our previous discussion is the same thing, that it's plus or minus 1. So they must be equal, and they must be plus or minus 1. So that's C2. So it means that D pi is an isomorphism again. This is 6-dimensional, that's 6-dimensional, so it's 6-dimensional. and implies the covering as before. So I wrote down explicitly a twofold cover of SO4, the universal cover. Because it shows also that pi 1 of SO4 is Z2, right, because S3 is simply connected. I can now ask the same question as before. Say, what are Lie groups with Lie algebra SO4? Right, so we now have a model which is simply connected. This and this have the same Lie algebra. It's a covering after all. So what's the center of the simply connected one? That's now Z2 cross Z2, plus or minus 1 in each component. So that's the center. So it has order 4. So I can define various subcovers. One is when I divide by the Z2, which has a minus 1 in both components, I get SO4. And of course now I can do there are other subgroups in here. Well, this group is Z2 plus Z2. Everything's an involution. The only subgroups are isomorphic to Z2. So I can take any subgroup here inside Z2. And as I take everything. But certainly I can do this first. And so one of them would be S3 cross S3 divided by plus or minus 1, 1. So that's 1Z2, which is different from the SO4 there. And I could do the other one. Are they the same? Pardon? It's SO3 times S. Oh, okay, maybe that's true. Yeah. So the same then, and the SO3 times S3. So that's how I can divide by Z2. But of course, what I now want to see is this really a different Lie group? They have the same Lie algebra, the twofold subcovers of S3 cross S3, and they have the same pi 1. Right, so pi 1 of SO4, so SO3 Z2. Which we're going to show in a minute, so that's not hard to see. So same pi 1. What about the center? What's the center of SO4? So what commutes with every orthogonal matrix? It's an obvious one.
We always have plus minus identity.
So minus identity commutes with everything. And the claim is that's it. So here I claim the center is just plus or minus identity. Don't know what the easiest way to see that is. Has to compute everything, so I just exhibit enough matrices. So for example, write R4 as R2 plus R2 in various different ways. Rotate here with different angles. These are eigenspaces kind of. If it commutes with it, it preserves the eigenspaces. And I do that for any decomposition, and then it must preserve each different two-dimensional subspace inside R4, so it's minus identity. So that's for SO4. What's the center for SO3 cos S3? For S3, you already saw here it's plus or minus 1. But what is in the first component? Just identity, right? The minus identity commutes with it, but doesn't lie in SO3, lies in O3. So it's just the identity. That's trivial center. In fact, we already saw that, right? The 2 for cover SO3 was S3. It had center Z2 and divided by the center, so I get no center. If you want to have the same center, right? Isomorphic. So same D algebra, same fundamental group, same center. And that's the question, are they the same group or not?
So SO4 quotient by the Z2 is SO3 times SO3?
No.
SO4.
So what is that? So I divide by the center of SO4, that's again another D group.
Yeah.
Right, so I can describe this as turns the universal cover. I divide by the whole center. Right. And when I divide by minus 1, I get SO4. And
SO3,
that's SO3, therefore. Correct.
The deck groups are isomorphic by an outer automorphism. Can we conclude from that the functions must be isomorphic?
What does that mean? So you're right, there is an outer automorphism switching the two factors of S3. What does that imply? It implies which two groups are the same. It implies these two are the same. Right? But we already saw there were SO3 cos S3, so it's not surprising.
No, but only also SO4.
You claim this is SO4? Well, for SO4, I divide by minus 1, right? And here I divide it by minus 1, 1. The one automorphism you say it takes minus 1 to itself, not to minus 1, 1. Okay, so that doesn't do it. But you can certainly ask the question, is there some other automorphism which takes minus 1 to minus 1, 1? Right? Is there such an automorphism? The answer is no. There isn't. If you think about it in terms of automorphisms, one has to think about this. I think this is a homework problem. That's one way to do this. Maybe that's a good exercise. Determine the automorphisms of S3 cos S3. What do they do in the center? Right, that's one way to solve the problem. But when I posed this problem in a course I taught at Penn a long time ago, like in the beginning course on manifold theory, so I asked that question, deliberate Lie groups, and someone came up with a neat idea to show they're different. So this is something I would have never thought of. Maybe trivial. It's nothing to do with covering. You don't need to do anything. You just need to know what orthogonal matrix is. So look at the subgroup. Or look at the elements, sorry. Look at the elements in each group. So column A. Subset A squared identity. So involutions. We'll get set of all involutions in each group. Let's see if we can determine what they look like. Let's start with SO4. What do involutions in SO4 look like? So rotation to square the identity.
We have identity dimension 2, minus anything dimension 2, but they can be
Any subspace? Why is that everything?
what's that?
Why is that everything? So another, what he was saying was, take a two-dimensional subspace in R4, take its orthogonal complement, don't do anything here, and multiply -1 here. That's clearly orthogonal and the squares identity. And so that's take V, orthogonal sum V, and on V it's a plus identity, and on W it's minus identity. Why is that everything? Linear algebra. What do such linear maps look like? What can you say about such linear maps? Normal forms of involutions. What are the eigenvalues?
Okay. Roots of unity of order 2. Plus minus 1.
Plus -1. Eigenvalues are plus -1. That's the first thing I can say.
And then you have determinant 1.
So the only question, so it could be, what's the dimension of each eigenspace, right? If that was two-dimensional, that's what it is. +1 eigenspace, -1 eigenspace. There, you can show they're orthogonal to each other because this A is an orthogonal, is in rotation. And what if one is one-dimensional, the other one is three-dimensional? That doesn't lie in S4, right? Say, if it's minus into a one-dimensional space, plus into a three-dimensional one, that's determined -1, and conversely. So these must be both two-dimensional. So what does it look like? I claim this is a Grassmannian. Two planes in R4. Because if I know one of them, then the orthogonal complement the other. So it's called the Grassmannians in R4. Very nice manifold. Okay, so that's on one side. What if we do on the other side? SO3 cross S3. What are involutions? What are involutions in this group?
So those are the involutions that are in the identity, norm minus identity.
Say that again?
In the comparabilization by Grassmannians, we don't have identity and we don't have minus identity.
Ah. Indeed. Absolutely. It has three components. Thank you. And that's the only other possibility. And then the whole eigenspace is four-dimensional. Okay, so it's 2 points and a Grassmannian. How about here? So now what are rotations on 3 space? What do they look like? The square identity.
For the same argument, it will be RP2. The ones that correspond that to the two-dimensional subspace.
So what do they exactly look like? Okay, so the eigenvalues are plus or minus 1, because now it's three-dimensional, so
I can have a two-dimensional subspace where I do minus identity, and the other one must be fixed identity.
right. Or again, the whole, okay, they can't be both of minus identity because you're in SO3, where the term will be minus 1. So in SO3, I get, so B2 plus W1, right? And here it's minus identity, here it's plus identity. So what is that topologically?
G23 or RP2?
RP2, yes. Determined by the plus 1 eigenspace. That's the direction inside R3. That's an RP2. And what are the involutions here in S3? Quaternion whose square is minus 1, maybe plus or minus 1. So that means there are two components. One RP2 minus one RP2. So two components in involutions, three components in involutions. Oh no, sorry, that's two also.
This is the product in that case.
It's also two involutions. So it's two. They both have two components. But yeah, so it's a product, right? So this here is RP2 because that's a better way to write this here. And this here is Grassmannian cross Z2. But is there another way to distinguish those two? That looks bigger, right? This is two-dimensional. And how big is that thing over there? Two planes in R4. How can I characterize a two-plane in R4?
Four-dimensional.
Yes, should be four-dimensional. Why is that?
You give a 4x4 matrix. You will have two columns of zeros. You can normalize the first 2 times 2 minor to be identical.
Let's see, how do you get the matrix? Say it again.
I take the generating matrix out of R2 into R4.
Or take a basis of the plane.
Yes, the basis.
Uh-huh.
And I choose a singular minor, so then I can normalize it to identity, and the remaining 4 coordinates will be the local chart.
Okay. Yeah. So this has dimension 4. And this is dimension 2. The cube proof. This was clearly an algebraic. This was not a geometer. He went into algebraic geometry, in fact. So set involution has nothing to do with the legal structure, right? It's just as a group. I don't care about the manifold structures. As a group, they can't be the same because a set of group elements, which are involutions, have different dimensions. A beautiful proof. Okay, so
What proof did you wait?
pardon?
You probably waited some other proof when you proposed this problem to your students.
Yes, I mean the proof that he had in mind, right? He wanted to see that these are some automorphism which takes -1, 1 into -1, -1. If there is, they're isomorphic, right? If there isn't, then just you have to argue, well, if these groups down here would be isomorphic, then I can go to the universal cover. Suppose S3 crosses 3. This isomorphism would lift to an automorphism upstairs. And it's only well defined if it takes kernel to kernel. Kernel here is -1, -1. Kernel here is -1, 1. So it's isomorphic if and only if there's some automorphism in S3 crosses C which takes that to that. Now I have to think about what do automorphisms possibly look like. Can they do that? And get a contradiction. So that's the proof I had in mind when I assigned the problem. Okay, so the only thing I still want to do before I go back to general theory is to show that for SO5, pi1 is also equal to 2. The two-fold cover is sp2. And for SO6, again, the two-fold cover is known, is SU4. So pi1 is equal to Z2, and these are both simply connected. There's a two-fold cover. So that has a very beautiful geometric argument. In general, for SON, one knows that pi1 is Z when n is equal to 2. Then it's SO2, that's just a circle. And Z2 when n is bigger than 2. So it means there must be a universal cover, SON tilde, which is a two-fold cover. Right? And these are what are called the spin groups. And they are a little bit difficult to describe in arbitrary dimension, but in low dimensions, I told you what they are. Right? So SO3 perp, or spin 3. Universal cover SO3 was S3. Universal cover SO4. That was S3 plus S3. Universal cover SO5. And that's just this. If I can show this simply connected, it would be sp2. Because it has to be, since it's a two-fold cover. And then for SO6, it's SU4. And for any value bigger than that, it's a Lie group, but not in anything not anything familiar, like orthogonal unitary symplectic group, nothing of that type. It's really a new Lie group. It's also a matrix group, but then I have to make the matrix huge. The size is 2 to the n. So the spin n here, this universal cover here, I can write as a matrix group on a vector space whose dimension is 2 to the n. So it's very large. I can talk about this at some point. Okay, so this Friday I was going to make up one lecture, right? So there's a lecture this Friday from 1:30 to 3 in this room. So that's the only room where we can take the lecture, so we'll be in this room, 1:30 to 3. And maybe next week we'll do some exercise again. And then at some later point I can make up another lecture. So on Friday I'm going to prove this thing here, and then talk the general structure of nilpotent and solvable Lie groups and Lie algebras. So we go back to general structure theory since we've seen enough examples now. Okay, that's it.